All right, it's 2 2. Let's get started. So hi there, welcome to Ask Seminar series. I'm John's seminar coordinator. So I will be moderating the seminar with Kathy, our communication manager. So a couple of housekeeping. The seminar is being recorded, and we will post the recording on our YouTube channel. And after the presentation, we'll have the Q&A session. So please feel free to bring up any questions you may have. We encourage you to speak up. If you don't have a mic, you can also chat us the questions, and we will read them out. And before the speaker gets started, I will hand the ball to our director, Nas Peter, to introduce the speaker. So, Nas Peter, please go ahead.
Thanks very much, John, and welcome to today's Essex seminars to all of you online. And a special welcome, of course, to Meghana Ranganathan, today's speaker. Meghana got her PhD from the MIT in the Department of Earth, Atmospheric and Planetary Sciences. And after that, she was a NOAA Climate and Global Change postdoc at Georgia Tech. And she is now assistant professor at the University of Chicago in the Geophysical Sciences Department. And her field is the interaction between glaciers and ice sheet, and that's what she's going to be talking about today. We all know that there's a lot of interest in ice sheets all over the world because as the ice sheet dissolve or melt, we all get to share in the pain because it's intimately tied to sea level rise. But it's not as simple as just a warmer world will melt the ice and raise the sea level. Most of the mass loss comes through the outlet glaciers that you can think of as sort of big rivers of ice that flow into the ocean. But the flow at a certain point doesn't become flow anymore. The ending is more dramatic. The glaciers break up, and the interaction between that breakup and the flow, I think, as I understand it, is what Meghana is going to talk to us about today. And we need to understand that in order to sort of get a better handle on where the sea level is really going. I think that's enough rambling from me. Over to you, Meghana.
Yeah, thank you so much for that introduction, and thanks to the organizers for the invite. I'm really excited to share some recent work that me and my group have been up to. I'm going to share my screen and launch, but let me know if for any reason you can't see my screen. Otherwise, I'm going to proceed as if everyone can see it. As Lars mentioned, today I'm going to be talking a little bit about this coupling between flow and fracture and ice sheets, and the kind of large scale motivation for this is we're really interested in how much ice that ice sheets and glaciers are going to eject over the next few centuries, because it has this direct implication for sea level rise. So this image is from from the last IPCC report, and consolidating all of our current estimates for future sea level rise between two. I'm showing right now two different SSP scenarios. Obviously, SSP scenario in which we take very aggressive climate action produces much less sea level rise than if we take very little climate action, and we have a much higher radiative forcing, we get much more sea level rise. So clearly there is going to be some variation in these estimates based off of what just societies are going to do. As a glaciologist, what I'm particularly interested in is the error bars for any given scenario, which, as you can see, are quite large, especially large for the scenario in which we take very little climate action. We're looking at anywhere from out to 2300, anywhere from just over 2 meters of sea level rise, all the way up to more than 5 meters of sea level rise. And that's an enormous range of uncertainty that, as glaciologists, we are very interested in trying to constrain as much as we possibly can in order to produce somewhat constrained and predictable estimates that we can pass over to decision makers who will be preparing our cities for future sea level rise. So when we're interested in constraining this uncertainty, it's worth it to ask where this uncertainty is coming from. And that's what these subplots are showing, which is the contributions from different polar regions. So Greenland, Antarctica, and then all of the other glaciers in the world. And what really stands out is that Antarctica in particular, both Greenland and Antarctica, but Antarctica kind of predominantly has enormous ranges of uncertainty around its future contributions. And a lot of this comes from just a fundamental incomplete understanding of a lot of the underlying dynamics associated with ice loss from Antarctica. And so that's what I'm going to be talking about today. And the introduction really nicely set this up in that the fundamental processes that are governing that ice loss from Antarctica are twofold. There is the kind of viscous flow of ice from the center of the ice sheet out to the margins, where, at least in the case of Antarctica, the ice hits the ocean and starts to float on top of the ocean, creating these big ice shelves or these floating extensions of ice sheets. And then at that point, it starts to fracture, and it fractures to create, crevasses or fractures within the ice, but then also to produce these calving events that eject icebergs. And it's the interplay between these two processes that really governs the ultimate mass loss from Antarctica. It's how fast the ice can transport down to the ocean, and then how fast and to what extent the ice starts to break up once it's reached the ocean. And so what makes this a really interesting scientific problem is because ice basically has this kind of dual behavior of behaving like a very viscous fluid over these long time scales. And you can see this in this Piedmont Glacier. This glacier is kind of spilling out between these mountains, flowing like honey, and producing this kind of circular feature. But then in very short time scales, it behaves like a brittle solid. And this is this big rift through the Larsen C ice shelf to show the magnitude and the extent of some of these fractures in Antarctica. And so from a physics and modeling perspective, this is this really interesting problem of ice kind of operating the intersection of two what's typically thought of as somewhat disparate sections of physics, which is fluid mechanics and solid mechanics. And as glaciologists, we really have to care about both behaviors and the coupling or the intersection between those behaviors. And that's something that I'm going to touch upon today. Just to kind of illustrate what all of this even looks like, I'm going to show this brief video of Pine Island Glacier. It's this glacier out in the western part of Antarctica, right here. Particularly impactful because it's accelerating rapidly. It's accumulating a lot of fracture as it accelerates, and it's in this region where we're concerned about possible instabilities within Antarctica. So it's of particular interest that we want to understand what's going on with this glacier. And I'm going to focus on this glacier for the vast majority of the talk. So we're looking at the terminus of the glacier, or the very edge. So everything that kind of looks white is glacier. Everything that looks darker is ocean. And as video plays, you're going to see this glacier advance and start to break up. And so what it's doing are these two behaviors of flowing out to the ocean and then starting to accumulate these fractures. And eventually those fractures propagate to produce icebergs that kind of hang around in the area in the vicinity of the glacier for a bit, and then eventually float out through ocean circulation out to the ocean. So there's a couple of things that I really want to touch on in this talk. And the first is, if you watch the margins of the glacier, so the kind of lateral edges of the glacier, what you can see is over the course of this time period, accumulation of what I'm going to call damage, or these really small scale fracture features that are kind of trying to destabilize some of the lateral edges of the glacier. And that kind of still accumulation of damage is very interesting because it is both seeming to accumulate in regions of rapid deformation, so where the ice is flowing and deforming really rapidly, but it also is kind of structurally weakening the ice and allowing the ice to flow further. So this is kind of this evidence of this coupling behavior between flow and fracture. As ice starts to flow and deform, it accumulates these fractures that structurally weakens the ice and enable it to flow even faster. And so I'm really interested in understanding what drives this behavior and ultimately how we can model this and incorporate this into our understanding of the future of glaciers like Pine Island. And kind of as our final setup for the problem at hand, what's really interesting again about this problem is that it occurs at these varying spatial scales. So what I just showed you is this kind of large scale look at this glacier Pine Island and the fractures it's accumulating. But if we were to take a bit of that ice and zoom in even further, what we would see is an accumulation of lots of little ice crystals. And so this is a sample of ice that's been taken as a thin section and put under a polarizing microscope so we can visualize all of the ice crystals and the orientation of those ice crystals. So this scale, I'm going to touch upon in this talk today, how this scale kind of governs some of that coupling behavior. Of course, we can zoom in even further to the molecular scale and really ask these questions about how the dynamics of the individual water molecules and the bonds between them affects fracture. Because ultimately, what is fracture? It's just the breaking of these bonds between these molecules in the lattice. So I'm very interested in how this coupling behavior occurs at these varying scales. So that's what I'm going to talk about today, is how flow and fracture are coupled across these scales, and ultimately what impact this coupling is going to have on ice sheet behavior. And I'm going to touch upon three kind of sub questions as I go through this talk. The first is just, how is damage accumulating in glaciers? To what extent is this driving? What is driving damage accumulation? Where is it occurring? How can we use that to understand the conditions that ice fractures in? Second question is then, what is this effect of this fracturing on mass loss and ice viscosity? And finally, I'm going to touch on this question of this coupling between viscosity and fracturing. So we're going to start today with actually the project that's most in progress, which just made sense thematically. So bear with me, this is still very much in progress. But we were interested in quantifying how much this damage is actually accumulating on glaciers for two reasons. The first is this tells us a little bit about the conditions in which ice fractures, gives us some insight into the physics of the system, but also we're interested in producing a data set that we can use to test models. So this project right now is being driven almost entirely by an undergraduate student named Anjali, who is a senior at the University of Chicago right now. She's been working with me for about 1.5 years trying to answer this question of, can we quantify how much damage or how much fracture is accumulating on Pine Island Glacier, which is the glacier I just showed you in that video. So these are some snapshots of this glacier from 2018 and 2020. There's a couple of key regions that are accumulating fractures that we are really interested in digging in further. So the first is this kind of lateral edge that we're going to call the northern margin. These edges you can see delineated by these regions of kind of increased blue. So this northern margin has been accumulating these fractures over the last, I think, 5 or 6 years, pretty dramatically. We were really interested in kind of quantifying when that started to happen, and to what extent. We've also been seeing increasing fractures kind of at the center line towards the upstream edge, so near where the glacier is grounded at the ice. And we think this has to do with the fact that the glacier is running up against kind of a high in the bedrock. And as the glacier flows over that, it experiences elevated stress and is starting to fracture. So you can see these fractures start to develop, and we think ultimately they're going to propagate downstream and further impact the whole ice shelf. And then there's this really dramatic increase in damage towards the southern edge of the margin, which is actually destabilizing this margin. And we can see clear evidence of accumulation of acceleration in the flow because of this region of increased damage. So we also wanted to quantify this as well. And then a similar thing is happening in the other margin, this accumulation of fracture. So there's all of this really kind of interesting regions, and we wanted to answer two questions. The first is, can we quantify this damage accumulation? Can we just say how much damage has been accumulating in the time window? So we're looking between 2018 and 2024, so just 6 years. And then we were also interested in addressing the question, under what stress regimes does damage accumulate? So is damage accumulating in tension, meaning the ice is being pulled apart, or shear, which meaning the ice is shearing or experiencing shear stresses, or is it being compressed, which is pretty rare in ice sheets generally. So to give you a sense of how we did this, we're employing this damage detection algorithm that was published by Micah Izabud a few years ago. Essentially, the way the algorithm works is it takes an image, a processed image of a glacier. So this is Pine Island Glacier from 2018, and it uses pixel intensity as a proxy for crevasses or for fracturing. And I'm happy to address any questions about how this algorithm works. But ultimately, what it does is it transforms this image into some estimates of fracturing. And so what we're looking at here is a color bar of both where fracture exists. So everywhere where you're seeing these yellow colors is where the algorithm is picking up fracturing. But then there's some color gradient. So darker red colors are more intense fractures, or potentially deeper or more concentrated fractures, and lighter images are less intense fractures. So we were able to use this algorithm over 6 years, 2018 to 2024, to quantify how much damage has been evolving in time. And so we produced these estimates from 2018 again to 2024. And this provides us at least a starting point to start to ask the question, quantifiably, how much has damage been increasing, especially in different regions of the glacier. So what we can see from 2018 to 2024 is an obvious expansion of damage, both spatially and also in magnitude. So 2018, you had a pretty confined region of damage that's since extended further upstream, so closer to where the ice is actually grounded to the bedrock. And a lot of regions has been increasing this in damage intensity. So we can see this most dramatically in this upper region of the southern margin, where we're seeing this kind of really bright red towards the later years. We're also seeing in those same regions I showed you where we were interested in evaluating these kind of northern margins. This upstream region is accumulating damage. The center region has been accumulating damage, we think, again, because of that high in the bedrock. So we're actually able to quantify these things that we were mostly just seeing by sight previously. By quantify, I mean we can do a subtraction from damage field in one year to the damage field in the other year and get a change in damage estimate. In this case, we're looking at change in damage accounting for advection, in which anywhere that you can see some red is damage accumulation, and anywhere that you see blue is damage reduction. So we can see that from year to year, we're mostly seeing damage accumulation, especially in the margins towards the terminus of the glacier. There's a handful of regions where we're seeing some evidence of damage reduction, which may mean healing or closing up of cracks. But for the most part, year by year, we're generally seeing accumulation of damage, and it's something that we can quantify. So that's kind of that first question we wanted to ask, which is how much has damage been accumulating? The next question we wanted to ask is under what conditions? So in what kind of stress regime do these damage regions seem to be accumulating damage in? And so we can break these different regions of damage down by stress regime. And by that, I mean, where is the ice sheet, where is the ice shelf in tension, where is it in compression, and where is it in shear? So what we're seeing here is over the course of a few years, where damage is colored by the stress regime. So gray is a shear, so a damage opening up in shear. Red is tension, and blue is compression. And generally what we've been noticing as a field for the last few years is that Pine Island Glacier has been transitioning into a mostly tension regime. As the ice shelf kind of structurally weakens, it's pulling itself apart much more dramatically than it was even 10 years ago. And we're seeing that represented in the damage field, which is more and more damage seems to be occurring in tension or in this pulling regime. But we're still seeing significant regions of damage in these marginal regions that are opening up in shear. So suggesting that there's kind of two regimes that are really appreciably contributing to fracture accumulation, shear fracture and then tensile fracture. And kind of the next stages of that discovery is to think a little bit about what the mechanisms are for a tension fracture versus a shear fracture and how we can incorporate that into models. But this is a little bit nuanced. So we've been trying to see if we can track any changes in time of these regions. So what I'm showing here are two different ways of kind of visualizing these different stress regimes and how they're affecting damage accumulation. On the left, we're looking at of all of the damage over all of the ice shelf, how much of that damage, what percent are in these different stress regimes? So shear, compression, and tension. These all numbers should add up to 100%, which should be all of the damage pixels. And so what we're seeing is fairly consistent over time, which is shear fracture generally dominates all of the damage. And that seems to be, again, keeping pretty consistent over our time period. Tension is also fairly consistent as the next level of damage. And compression is a pretty small fraction of the overall damage, which is unsurprising given that ice is very strong in compression and comparatively weaker in tension. So of the damage regions, most is occurring in shear, and that's pretty consistent in our time period. However, if we were to think about this slightly different, we think of the stress regime, so like of all of the pixels that are in tension, what percentage of those are damaged, the picture changes a little bit. So what we see is that of these tension regime, more and more of the tensile regime in Pine Island Glacier is becoming fractured. So starting at 15% in 2018, moving up closer to 35% over the last few years. There's an uptick as well in shear and compression. More of those regions are becoming damaged, but not quite as dramatic. So within each stress regime, the tensile regime generally is the most fractured. So there's a little bit of nuance there. It's very clear that both the shear and the tension regime are important to understand, but there's this clear increase in tension fracture in Pine Island Glacier that we really want to understand better in a modeling regime. The final thing that we wanted to do is actually quantify under what stresses ice is fracturing. And there's a couple of reasons we want to do this. First, we want to just ask the question, is this damage accumulating because stresses are increasing on the ice shelf. But we also want to nail down exactly at what stresses ice fractures. And the rest of this talk will be focusing on exactly why we care about that number. But really, it's the main input into our models for ice fracture is what is the stress threshold at which ice starts to fracture. So we want to see if we can see that in our data. So here, what I'm showing you is some histograms of the first principal stress, which is just a way of kind of looking at one of the average stress states of the glacier. The green histogram is where damage isn't changing very much. So these are the stresses at which you're not seeing accumulation or reduction of damage. The blue histogram is where we're seeing accumulation of damage. So all the stresses at which damage appears to be accumulating, and the red histogram is showing where damage is reducing. And this is in stress space, as we can see below here. So we were interested in seeing, is there a distinction between the stresses at which damage is not changing much at all and where damage is actually accumulating? So we can look at these in like a box plot framework. So here's where damage is not accumulating or reducing, just kind of staying constant, versus where damage is accumulating in blue and where damage is reducing in red. And what we can see is a very slight shift. Damage staying constant is ever so slightly lower stress than where damage is accumulating and when damage is reducing. We did a very quick statistical test called the Cliffs Delta test, which is just a way of determining whether there's a significant difference between two distributions. And what we found was that there's a somewhat significant difference between the distributions of where damage isn't changing and where damage is reducing. And similarly, a somewhat significant difference in the stresses at which between damage staying the same and damage increasing. Interestingly enough, there's not a really significant difference between the stresses at which damage increases and decreases, which is something that we're still kind of working out exactly why. The physical explanation for that is basically the stresses at which damage fractures produce and fractures heal appear to be fairly similar. But the exact physical mechanism of that, I have speculations on, but no real explanation yet, as we're still digging into this. The next thing we wanted to check is whether these histograms or these kind of estimates of these stresses are changing in time. The answer is not necessarily significantly. There's a slight shift possibly to higher stresses in time, resulting in a slight shift in where fractures are accumulating. The stresses at which fractures are accumulating appear to be increasing, but it's not obvious yet. It's something we're still digging into. So I mentioned that this is the most preliminary of the stuff that I'm going to talk about today. We are still working on this and hoping to wrap it up relatively soon. But the main priorities for us in continuing along this line of research is trying to quantify these stress thresholds or these thresholds at which ice is fracturing. There is kind of fracture mechanistic ways of quantifying these differences. And so we're actively working on that now, but really just drawing a line between the stresses at which ice does not seem to be fracturing much and the stresses at which ice is fracturing. And that's something we're hoping to do, both to estimate what this number is, but also see if it's changing in time. And the second thing we're trying to do is look at other regions and compare, is Pine Island Glacier uniquely accumulating this fracture, or are there other regions that are behaving similarly? So we're looking at two regions in particular. One is the Drgalski Ice Tongue. We're interested in this region because it doesn't really have strong shear regions like Pine Island. It's really mostly just in tension pulling itself apart. So it's behaving slightly differently. So we've started preliminarily accumulating these damage estimates in time and not seeing very much increase in the Drgalski Ice Tongue. We're interested also in Bird Glacier. Bird has really strong shear, but it's laterally confined by mountains, as opposed to Pine Island, which isn't really confined laterally by any obvious topography, at least not as dramatic as these mountains. And so we were curious if that lateral confinement makes a difference. And so we're seeing increase in damage, but not significantly, not anywhere near Pine Island Glacier. So we're going to do some comparisons to see if we can understand why Pine Island is behaving so differently than everywhere else. But this is all still in development. Ultimately, what we can take away right now is that damage, and especially in Pine Island Glacier, is clearly accumulating strongly in shear and tensile regimes at somewhat elevated stresses. And we still need to dig into this further to understand the physics and the modeling implications of this. So that's where I'm going to leave that and turn to this question of, well, if damage is accumulating, if fracture is accumulating, what effect does this have on ice viscosity and mass loss? How can we couple this to ice flow? And that brings me to actually define a term that I've been throwing around, which is damage, and how that is distinct from fracturing. So the idea of damage is it comes from some materials, the world of material science, and which was trying to solve this problem of the fact that fracture is a fundamentally discontinuous feature. There is a fracture and then there is not a fracture, and there really isn't a continuum between those two. But we are interested in the effects of fracture on flow, which is a fundamentally continuous variable of velocity. So this is a way of kind of putting fracture into a continuous state variable. So damage is this continuum state variable that essentially is describing how much the macroscopic properties of ice reduces due to cracks. So you can think about this almost as an average of how much fracture is in some volume of ice. So this damage variable D goes from 0 to 1, 1 meaning that volume of ice is entirely fractured. It has no longer any load-bearing ability at all because it's been so damaged. Damage variable D of 0 means that it's a completely intact sample of ice. So it has all of its stress-bearing properties because there's basically no fracture in it. So 1 is maximally fractured, 0 is not fractured at all. And this is the way we typically model the effect of fracturing on flow in ice sheets because it's our way of putting fracture into an otherwise continuous model. The way that we then feed this back into affect flow is by essentially penalizing ice viscosity. So we have our way of calculating ice flow as the relationship between how rapidly ice deforms and applied stress. And this relationship between stress and flow depends on ice viscosity, so how viscous the ice is. So that is this eta parameter, also this, I wrote this out in words, and we can penalize ice viscosity by this damage variable D. Essentially, when D is very, very close to 1, so ice is incredibly fractured, we end up with a very, very low ice viscosity. So ice that basically can't support very much stress at all, and so flows very rapidly in response to stress. When D is 0, then you have your regular intact ice viscosity. Viscosity is much higher. And this is the way that we couple damage or couple fracture into our ice flow models. And people have used this framework as a way of trying to make this point that damage or fracture is affecting flow pretty significantly. One kind of very clear paper that has noticed this is this paper from 2023 that was looking at Pine Island Glacier. So this is that same terminus of Pine Island Glacier that we've been looking at, Anjali and I. And they were looking at what we're going to call ice softness. It's essentially an inverse of ice viscosity. So how soft the ice is. And they found this just by using an inverse method. And they essentially inverted for ice softness from 2017 to 2020. And they noticed that ice was getting much softer in certain regions, in particular in these margins right here. And they attribute that to the increase in damage, because if you were to zoom into what these regions actually look like between these 2 years, in 2017, you've got a few fractures, but a few pretty clearly defined fractures. In 2020, that margin is basically almost fallen apart. And they made this point that you can actually see that in the velocity field and in estimates of ice viscosity, because we can see this increase in softness. So there's clearly something at play here that is feeding the effects of fracture back into the flow field. And we really want to be able to model that and understand what effect that has on mass loss. So the way we model that is by taking this damage variable D and evolving it in time. And we evolve it in time based on the simple transport equation. Change in damage with time plus the advection of that damage is equal to some source term, F. And that source term kicks in when stresses reach a threshold. This is back to that threshold that Anjali and I are interested in constraining with those damage estimates, damage observations that I was showing you. When stress exceeds this threshold that I'm going to call sigma T, or the strength of ice, you accumulate damage. Anywhere where stresses are less than that, nothing happens. There's only transport in this equation. What that means is that this stress threshold is basically the most important parameter in damage modeling and fracture modeling, because it dictates where, under what stress regimes, we should even start to think about ice fracture. So I'm going to show you some just simple runs to show you what effect damage might have on ice sheet mass loss using an equation similar to this, focusing on Pine Island Glacier, which is this glacier that, again, has been increasing, accumulating in damage. And so we set up a pretty simple simulation of Pine Island Glacier using observation. So this is the observed velocity field. Pine Island Glacier is flowing at about 4,500 meters per year. From upstream down to downstream, would be all ocean. And we force this simulation with observed basal melt rates. So we're essentially using observations to force melting underneath the ice where it's in contact with the ocean. So this is what the basal melt rate looks like. Of course, it's zero wherever the ice is in contact with bedrock, but where the ice is in contact with ocean, there is some melting that happens. This is our climate forcing, essentially. And we just wanted to make the point that including damage in the simulation enhances mass loss. So to make this point, we first run a control simulation in which there's no damage. The only thing that's affecting Pine Island Glacier is melting from the ocean. And in that case, Pine Island starts with some ice volume and it decreases in time over this 300-year run. Then if we kick on damage, what we see is about a 30% enhancement in mass loss due to this effect of damage. So as the ice starts to flow faster because of ocean forcing, it accumulates these fractures. Fractures weaken the ice, allow it to flow faster, and you get this positive feedback. And that ultimately ends up enhancing ice mass loss by about 30%. Of course, this uncertainty envelope is that uncertainty from that stress threshold. So what is the stress at which ice starts to accumulate fractures ends up being kind of the most significant source of uncertainty in the modeling of this feedback. So here I'm showing basically the full end member cases from no damage at all to damage is accumulating everywhere where the stresses are positive, which is this magenta line here. And the true answer is probably somewhere in between, depending on what that stress threshold is. But this is kind of the largest possible uncertainty that mass loss can have due to this damage evolution. And of course, this is all this enhancement to mass loss occurs because damage is accumulating. And so this is what that damage accumulating looks like over the course of that simulation. You're getting massive increases in damage in the margins, which is what Anjali's been seeing in her observations, and some damage accumulation as well in the center of the ice shelf. All right, so that answers the second question, which is what is the effective damage on viscosity and mass loss? What we're seeing is that the coupling and this positive feedback ultimately can result in around a 33% enhancement. But the true answer is probably less than that, somewhere between 0 and 33. And we don't actually know what the answer to that is. Ultimately, what that answer comes down to is needing to know what the stress threshold is. And that's what I'm going to talk about next is the importance of this stress threshold and how we can better understand it. Right now, it is treated mostly as the static parameter. We set a single number, like 100 kilopascals, and we say anytime stresses get above 100 kilopascals, we should see fracture. Of course, the real answer is probably more complicated than that. Ice isn't homogeneous. Ice, as I mentioned at the very beginning of this talk, is made up of all these individual ice crystals that have orientation and shape and all of this complexity that maybe we should be thinking about a little bit further. And I'm going to illustrate why all of that microphysical complexity might affect fracture with this little simple theoretical schematic. So I'm going to pretend a little schematic, a sample of ice. It's a polycrystal, so it's made up of lots of crystals, in this case 10. Each of these polygons is an ice crystal. And each of these ice crystals is a lattice. So these kind of hexagonal structures is the ice lattice. If we were to zoom into the boundary between two ice crystals, what that boundary looks like is shown in this green, in these green dots and lines here. Essentially, the difference between one ice crystal and another ice crystal is the orientation at which those ice crystals are in space. So when one ice crystal is significantly oriented differently from another ice crystal, we define those as two different ice crystals, or the lattices are at different angles from each other. So you can see that here. This lattice is at a slightly offset angle from this lattice. And so that's how we define those being two distinct ice crystals. And what that means is that the boundary in between those ice crystals is irregular. These are nice, regular, clear hexagons with regular atomic bonds and spacing. And anything in between them, because they're offset, is really irregular. Essentially, what that means is that this is the weak point of this ice crystal, of this polycrystal. If I were to stress this little sample of ice, bonds that are going to break are likely going to be the bonds along that boundary, because those are the weak part. Those are the irregular bonds. So grain boundaries essentially are these inherent flaws in the ice. If I'm going to sample this, if I'm going to stress this polycrystal, cracks are likely going to initiate along the grain boundaries because they are the weak point or the inherent flaw. And once initiated, those cracks are probably going to continue to propagate along those grain boundaries because, again, those are the weak points in the ice. What that means is that the length and the location of these grain boundaries end up being important for understanding when and how ice is going to break, and suggests that this threshold for ice fracture is probably not a single number. It probably varies, and it probably varies based off of the microphysics, how long those grain boundaries are, how oriented the different crystals are. Those are all something that we need to take into account. Essentially, what this means is that the stress threshold is more complex than just a single number. It's actually a function of a bunch of different microstructural parameters and material parameters. One example being grain size. So how big are those grains? How long are those grain boundaries? Some other examples being temperature. How warm is the ice? A warm sample of materials probably going to fracture less easily than a cold sample, which is going to be much more brittle. And it could also be a function of viscosity in general. So how viscous the ice is may play a role in what this threshold is between ice fracturing and not fracturing. So this is that coupling between ice flow and ice fracture that I was referring to. As ice flows, the microstructural properties evolve, viscosity evolves, and ultimately, I believe that that's going to influence how the readiness by which ice fractures open. So that brings me to my final point in this talk, which is what is the nature between the coupling between ice viscosity and fracturing? And I seek to make the point that this threshold actually should be a function of flow, or a function of the microstructural properties that evolve with flow. And this is not actually a new idea. There's been a number of laboratory studies that have shown the dependence on, for example, grain size. As grain sizes increase, this should have a y-axis label that says ice strength in megapascals, but they've shown a very clear reduction in ice strength as grain sizes increase. From our little schematic, we can kind of understand this as grain sizes increase, or the crystal size increases, grain boundary area is going to increase, so you have more region for those fractures to propagate because there's more region of flaw. So there's a very clear relationship. And so I was interested in seeing, can we put this relationship into a model for damage, evolve grain size along with evolving damage, and see if that influences estimates of mass loss. So essentially, from these laboratory estimates, we can get a constraint on what the strength of ice is as a function of grain size. And luckily, I actually have a model of grain size that I developed during my PhD that I can use to evolve grain size along with damage. Another way of thinking about this comparison is we want to understand a more complex coupling than what has been done before. So typically, when people look at the coupling between damage and flow, it's in this format. You have a static stress threshold, it feeds into the damage model, and the damage model kind of co-evolves with stress. As damage evolves, it feeds into the stress field. As the stress field evolves, it feeds back into the damage field. But the stress threshold always remains fixed. What I was interested in evaluating is if we bring in some of this more complex coupling. So for example, if we allow grain size to influence stress threshold, grain size meaning the size of the ice crystals, to influence the stress threshold, we get this big complex coupling where temperature actually influences the size of ice crystals, stress influences temperature, and the size of the ice crystals. All of that feeds into the stress threshold, which feeds into damage, which co-evolves with stress. It's a very complicated coupling, but if we set up a simulation that has this evolving stress threshold, we were interested in trying to address this question of, does it produce more mass loss than if we just use this fixed threshold like everybody does? And of course, there's also a control simulation where we have no damage coupling at all. So we revisit the Pine Island Glacier example, focus on just this kind of downstream region of Pine Island because the upstream region is probably not doing anything super interesting when we're interested in the accumulation of fracture. And then we set up an example simulation where we co-evolve grain size or the size of ice crystals with the flow. So this is the initial temperature field and the initial grain size field that we start with. This was just found by essentially spinning up to a steady state. And then we can feed that the temperature and the grain size into this equation that I found used from laboratory experiments to estimate an initial damage field. There's not very much damage here because, and I'll talk about this in a bit, but the laboratory constraints actually produce very, very large strength estimates, much larger than we think natural scenarios would have. But for now, the laboratory constraints are the best estimate that we have, so we're going to go with it. So we have a initial damage field, and we use that to start our simulation. So this is the control simulation where we have no coupling at all to damage. The only thing that Pine Island Glacier is doing is responding to ocean forcing, and ice volume decreases with time because the ocean forcing is melting the glacier. If we were to add a damage coupling, but we were to keep that stress threshold, this one here, fixed, we don't evolve it in time, we get a little increase in mass loss, just about 2% of an enhancement to mass loss. And we could track that in time. So how much mass loss is enhanced compared to the control simulation? It's very little. And it's very little likely because that stress threshold constrained by laboratory estimates is really high. It's somewhere on the order of like 0.5 to 1 megapascal, which are high stresses for a natural glacier. So that's producing very little damage and therefore very little mass loss enhancement. So very little change in damage over time. But what we're interested in is not the absolute values of these mass loss estimates, but how much more mass loss do you get when you incorporate this evolving stress threshold? So you allow the size of the ice crystals to evolve, that feeds in at every time step into a new stress threshold, which then feeds into damage. And if we were to incorporate that entire complexity of coupling, we get substantially more ice mass loss. Doesn't look as that substantial from this line, but when you compare it to the kind of experimental simulation 1 or with a fixed threshold, you get about a 4 times increase in the enhancement of mass loss. So about, sorry, this should say not 14%, but about 9% enhancement in mass loss compared to the control simulation, about a 4-fold increase in the enhancement of mass loss compared to just keeping a fixed threshold. And the reason that we get such a dramatic increase in mass loss estimates is because of this coupling that I mentioned. So essentially, as ice starts to deform faster because it is responding to ocean forcing, temperature increases. And that's just because as ice starts to shear, it generates heat. So as ice shears more rapidly, it's going to generate more heat. That temperature change, that increase in temperature, leads to a bulk increase in the size of ice crystals. And this is something that I worked on during my PhD, but we get kind of an increase in the size of the ice crystals across the whole glacier. That increase in the size of ice crystals reduces the strength of that stress threshold, so reduces the strength of ice and makes it easier for fractures to accumulate. So this is the reduction in the stress threshold, which is actually pretty substantial. It's about a 0.4 megapascal reduction in the stress threshold, and that allows for more damage accumulation. These numbers don't look dramatic because, again, we're starting with a pretty high stress threshold. But when we compare the damage change with grain size evolution to a damage change with just a static stress threshold, you get substantially more damage, and that's reflected in the estimates for mass loss. So all of this to suggest that what's going on the microphysical level, so the evolution, for example, of the size of ice crystals within a glacier, can actually have a significant effect on the bulk fracture accumulation, and therefore the kind of effect of large-scale fracture on flow. And so it's something that we need to investigate further and understand further, which is this the role of microphysics on ice fracture. And that brings me to this last point, which is what is the nature of the coupling between ice viscosity and ice fracture? And we find that there exists this two-way coupling between viscosity and fracture. So rather than this one-way coupling where fracture just affects flow, but flow doesn't really affect fracture, which is typically how ice damage is modeled, we suggest this two-way coupling where fracture is affecting flow, but then flow is evolving these microphysical properties, which is ultimately affecting fracture and the potential for ice fracture. So this can be explicitly modeled and it ends up resulting in enhancement to mass loss. Of course, this is an incomplete story. We were only focused on the size of ice crystals or grain size, and we pretty much ignored everything else, things like the role of temperature, viscosity. We were interested in incorporating the effects of, for example, temperature, and then going into the lab data, there just wasn't really a clear trend. There's very, very few studies that have looked at how temperature affects the strength of ice, and those studies don't seem to show any clear trend. This is likely because looking across these studies, they have very different experimental setups. They're using different ice crystal samples. They're using different samples that are created in different ways. They're pulling the ice apart differently. And so this seemed to us a reason for more experimental analyses before we can continue to model the full effects. This brings me to work that has not yet happened, but we're currently just getting off the ground. This is work, I should put his name, that I'm going to start up with a collaborator, Andrew Cross, at Woods Hole Oceanographic Institution. He's an experimentalist with a big rig that allows us to actually fracture samples of ice in the lab. And so this is a little example of his rig. And we're essentially going to do tensile strength tests. So pulling samples of ice apart and testing at which stress those ice samples break for very different properties of ice samples. So we're going to do that in two ways. The first is this kind of indirect test where you have a sample of ice and you squish it in one orientation and then it spreads out in the other orientation. And you get a kind of an indirect estimate for how strong the ice is in tension from that other orientation spreading. We're also going to do some direct tests where we're really just gripping a sample of ice and pulling on it. We've got some preliminary tests done from these, or really Andy's done these preliminary tests in these indirect tests and have shown that we can use these indirect tests to estimate exactly the stress at which ice ruptures, which is right here, hovers around 1 megapascal in this example setup. But what we're interested in doing is testing the effects of a whole bunch of different microstructural properties. So retesting the effects of grain size, but also different samples at different temperatures, samples with different ice fabrics, so the orientation of those crystals, samples with different chemical impurities, and just samples of varying sizes. And the hope is that we'll actually produce this kind of really wide range of data set of about 90 experimental data points that will give us kind of a really complete and very comprehensive, but also very consistent way of comparing the effects on fracture strength of all of these different properties. Ultimately, once Andy does kind of pioneers all of those experiments, I will take the data and using data-driven methods, so I hope to discover some form of this tensile strength or the strength equation that is more complex than just the grain size component, that has the effects of fabric, that's this EF, impurities, that's this EI, and this Arrhenius relationship, it will be the temperature effects. We're speculating or hypothesizing that it'll be some kind of Arrhenius relationship. So once we have this equation that's much more complex, we can even further complicate the look on this damage coupling by incorporating the direct effects of temperature and of fabric into this full coupling and test how all these different effects end up affecting this damage stress coupling. All of this is in service of trying to, again, understand really deeply what's going on in Pine Island Glacier. The observations Anjali's been using, we're hoping to use to actually benchmark some of these models that we create to make this point that you really need this two-way coupling in order to produce the damage that Pine Island gets from observations. But what's happening in Pine Island is quite complex, and we're hoping to really understand it further deeply. And again, ultimately, in order to understand the drivers of the mass loss from Pine Island Glacier and try to understand some of the uncertainty underlying mass loss from the Antarctic Ice Sheet, which will again ultimately be in service of trying to further constrain this uncertainty in sea level estimates. And this is the work that kind of a little taste of much broader work that my group is doing, trying to understand how microphysics and ice sheets ultimately affect large scale behavior. Trying to understand how these microphysical properties contribute to ice flow and ice fracture, how we can model those on really large scales, because our ice sheet models work on large scales, what effect these have on future projections, and then how we can use large scale data to benchmark some of these, kind of what Anjali's been doing. So thank you so much for listening. I'm happy to take questions about any of this.
Thank you. So if you have any questions, please go ahead and raise your hand, or you can type it in the chat and I will read it out loud. Yeah, go ahead, Monghan.
Thank you so much for your talk. That was very fascinating. I guess I have two questions actually. So the first one is related to the first part of your talk where you have this enhance of damage and also healing. And later on, you show this animation. It feels like there's sort of like a geometry difference between the west side and east side. So I was wondering where you are seeing the healing, whether there's change of thickness of the ice, or if there's a way to measure that.
Yeah, so the answer to your first question about where we're seeing the healing, a lot of it seems to be happening in the margin. So you can see this color map is a little hard to see. Anywhere where you can see blue is where we're seeing healing. So there's a little bit of healing, for example, between these years in the margins, kind of consistently
Yeah,
in the
that's
margins, a little bit of healing kind of upstream. So my best guess as to what's happening, assuming that this healing is real, which we're still testing to make sure this is not just noise. But if this is robust, my guess is that as ice deforms, ice deformation can close fractures, because you can think as ice deforms, it'll kind of deform over the fractures and kind of push them close. And so it makes sense to me that most of the healing is happening in regions of shear rather than regions of tension, because that's where ice deforms and therefore where cracks might close. To answer your,
Well,
can you
actually,
remind me what your second?
I haven't asked my second question.
Oh, go for it. Go for it.
So the second question is about your second part where you're introducing that sigma t, and you talk
Yes.
about the grain boundary. I was just wondering that when the ice is flowing from the continent to the ice shelf, it is a very anisotropic process where you have a
Hmm.
very high strain rate in one direction, but not so much in the other direction.
Yeah.
So I was just wondering whether that is going to contribute some kind of like specific like or additional parameter that regarding like the shape of your grain or how damage is going to happen in
Hmm.
one direction more so than the other direction. So in the end, whether your viscosity will be considered to be like anisotropic as well.
Hmm. Yeah, I think the answer is yes, but we don't know to what extent. And I think that's because we don't really, no, I have not found a single experimental study to look at how fabric affects fracture potential. So what
Mhm.
we do know is that, just theoretically, it makes a lot of sense that the orientation of those crystals should affect how far those fractures propagate. There
Mhm.
isn't really the data to back that up yet. And that's what Andy and I are hoping to do in the lab, is to generate some of that data.
Mhm.
Theoretically, though, you're right that as fabrics evolve, we would expect both the potential for damage to increase, but also the orientation of those fractures. And so the next thing that we want to do as we kind of further advance this damage modeling is to make the damage model itself anisotropic. People have done this before and shown that, there is a preferred orientation to fractures, in certain stress regimes, and so representing that could affect how fractures affect flow. So none of that has been done yet, but that's kind of the next stages of the work.
Thank you.
Yeah, thanks.
Go ahead, Aaron.
Okay. Oh my goodness. Thanks for the really awesome talk. I
Mhm.
was just wondering how the grain size is initialized in the model and
Mhm.
if remote sensing observations help to constrain that or if it's more of like a free running thing that depends on temperature. Um, that's my first question. I had a second easy follow-up question.
Okay. Yeah, it's yes, it has to do with remote sensing observations, but not directly. There's no real way that we know of for to remotely sense grain size because it's just too small. So the way we did this was we inferred ice viscosity, and we essentially spun up a temperature and grain size that were consistent with that ice viscosity. So temperature directly feeds into the grain size model. So if you can think as, you have a initial viscosity. So you spin up a steady state temperature that produces that's consistent with that ice viscosity, and then you produce a grain size that produces a damage that's also consistent with that ice viscosity. Then that's kind of your initialization. So it's this kind of iterative procedure. It is, technically correct, and it's correct in the sense that it produces consistent temperature and damage fields that both together produce an inferred viscosity. I would not defend it as the correct temperature damage fields that will match with observations. It's essentially a consistent temperature and damage and grain size field. And so we were really just interested in doing the comparison. We weren't trying to initialize things to a particular year and produce real projections.
Okay, cool. Yeah, that's what I had in my mind.
Mhm.
My other question was just about the damage viscosity relationship. So I was just wondering, so when damage goes to 1, viscosity
Yeah.
presumably goes to 0. Do you run into any like numerical stability issues with that? Because it seems scary to me, having not really dealt with it before.
Yes, yeah, you have to cut off the damage below 1 because otherwise you get dividing by 0 and it blows everything up. And yeah, that where you cut it off is a little bit finicky. It really, ideally, you'd want to cut it off as close to 1 as you can possibly get. But yeah, numerical solvers are going to have issues with that. So a lot of people tend to cut that damage off closer to like 0.9. Even some people have defended cutting it off even lower because the idea is once damage accumulates significantly enough, because this is like an exponential effect, the damage viscosity comes so close to 0 that any that representing damage even higher at higher values doesn't appreciably affect the flow field. But you have to cut it off at some point, and that introduces a little bit of uncertainty.
Thank you.
Yeah.
Travis?
Hey, Meghana, great
Hey.
talk. I was curious about if you could speculate as to the role of pore fluid pressure. I guess I'm thinking
Mhm.
about these kind of the recent papers by like Colin Meyer's group and looking at shear heating, and how much that melt in the shear margins contributes to the initiation of fractures and the accumulation of damage.
Yeah, so just to start that the answer with we're assuming completely dry fractures, so we haven't really touched the melt question yet. My speculation would be that there's I mean, based on our knowledge of hydrofracture, you would expect melt to kind of further enhance fracturing, depending on the extent of the melt. I think it's a kind of a complicated question because our picture of melt is a little bit hazy, and so as melt starts to generate, yeah, you're going to be opening fractures, but you're also starting to change the deformation regime. So you're going to be changing a lot of the microphysical processes that we're also interested um, in simulating. So it's not clear to me exactly what the effect is going to be, because I think it's more complex than just saying, oh, water accumulates, it pushes open the cracks, so it must enhance this effect. Because I think once you account for the melt effect on the microphysics, there's a chance it could counteract that effect. And I just haven't really nailed down in my own head which effect would win out, if that makes sense. So the short answer is I don't really know, but I think there's two things going to be happening: the direct effect on the fracture, and then there's the effect of the melt on microphysics, which then affects fracture. And I think I don't know how well we have constrained the latter effect, though I know a lot of people are interested in the effect of melt on rheology and deformation and microphysics. So maybe we'll start to put that together at some point soon.
Yeah, I was also going to ask a question about the kind of, I guess, transgranular fracture from,
Hmm.
really highly deformed and strong C-axis orientations in the fabric, but it seems like, you and Andy have already kind of planned those experiments, and yeah, excited to see the results of that.
Yeah, that's kind of the hope, is that we'll be able to get a sense of a whole parameter space of like temperature and stress, where we're seeing different modes of fracture, where we're seeing intergranular, intragranular, where fracture doesn't happen at all. So yeah, we'll see what comes of it, but we're very optimistic.
Yeah, and so from his experimental setup with the Brazilian test, it looked like you had kind of a backlight, or so you could kind of see where the fractures are initiating, whether it's grain boundaries or it's within the fabric of the ice grain itself.
Right, and the hope is we'll do actually cryo EBSD to actually see.
Yep.
We're hoping to be able to see the whether we can see where the fractures are propagating on, but we're also hoping to see if we can see evidence of different kind of small scale fracture mechanisms. So pileups of dislocations, grain boundary sliding effects, stuff like that.
Awesome. Looking forward to it.
Yeah, thanks.
Thanks. Well, we're at time now. Does anyone have one last question while we still have our speaker? Okay, well, thank you all for attending, and big thank you to Meghana for coming and giving us this great talk. As always, we're going to upload this video to our YouTube channel afterwards. It'll probably take a couple of days. And we're going to continue with our seminar series next week. So thank you so much.
Thanks, everyone.
Great. Have a wonderful afternoon.